save. All right. Last time we predicted and measured a 5'9" pendulum, and then went outside, measured time period of a 3-story tall pendulum. What was the final time? Like, what was the time period that we found for it? It's too big. What was it?
Like 50, 59 seconds.
Yeah, for total, so I think we came up like 6. I forgot what actual it was.
58 seconds, is that right? For 10 time periods? What did we find? $58. People agree with that? So time period was 5.8 seconds. Does that sound right? 5.8. Okay. T is 2 pi over square root G over L. What was the length? I went and measured the length, but let's predict. We know the time period. We have an equation with one unknown in it, just L. So what was L? Just doing the square roots in your head, or no? Squaring, no. How long was this thing? 32.2 is a good, like, feet per second squared, if we're trying to keep it in feet. Or go meters and then convert back, then we can convert back to feet, but
I got 27.4 feet.
how much?
27.4.
27.4? How's that confirm? Anybody else?
Yeah,
27.4? Okay. And then I gotta do a quick so 27 feet 5 inches is like our prediction based on the time period that we measured and kind of remembered. I think we remembered it pretty well. The length that I measured, like bring it down I like brought it down the hallway and like counted out how many squares, was 27 feet 8 inches. How are we doing? How close are we? Pretty darn good, right? Like 3 over, what is it? 3 over 27 times 12 plus, so we're maybe 1% off in our length calculation based on like experimental and measured results, 1%. So this stuff works. It's good. And time period, and you saw, like, as we were swinging it, there were other things happening. Like, the wind was blowing, like, there was other things, but natural frequency, it's called that because it's such, like, a stable value, and it keeps coming up. So if you're building, like, differential equations like this, and there is that term that is, like, a natural frequency term, it's usually very constant. Like, you'll be able to measure it through a lot of noise and other factors kind of coming in to play. Good to know. At least I think it's good to know. All right, so then wrapping up for, like, module 3 work, I wanted to take a look at, so I think these questions, like we talked about the last couple of classes about, like, what are the differences that we notice, like differences in time period or differences in amplitude. Like, that's a good way to look at a signal that's sine waves and cosine waves and say, this is what I notice. This is the measured difference that I have. So I think those we kind of covered. But this last one is kind of a nice segue into energy and momentum methods that we're doing for module 4 anyway. But thinking about what other calculations with all, like, we have all this information that we predicted, how else can we compare them? So did you think about that? What were you like thinking that you could compare? Yeah.
I was thinking maybe like if we calculated the energy and the kinetic and potential energies.
Yeah, all right. Okay, so for what is the conservation of energy, and I know you're all, like, in the throes of thermodynamics, maybe fluid mechanics. Is everybody thermo right now ish? Yeah, so you're all, like, deep into the confusing source of thermo. So in our case, what are the thermodynamics of a pendulum? Where's the energy coming from? Where is it going? What's going on here? Do we have internal energy? No? I mean, I guess technically yes, but at least no change, no measurable change in internal energy, okay? So U is gone. What else do we have? What other terms? Do we have work being done to the system? Yeah, I guess it depends. This one's kind of a pedantic question. What do you think? Work being done? Air resistance, but at least from when we said this is T, this is mg, our model works pretty well, like with two forces, just tension and gravity. So though at least tension's not doing any work on the system, gravity, do you want to call that work or something else? What's the other term?
Gravitational potential energy.
Yeah, like potential, we can call it like, and potential energy is work done. Like if you have a change in potential energy, work was done on the system. But if you're talking about like conservation of energy, the full, oh my God, now I have a T and then I'm gonna write another T. No. All right, anyway. All right, I gotta get rid of that T. I'm gonna call it reaction tension so that I can say T plus V plus work 1 to 2. So if we're talking about like the full, at least the things that we care about in dynamics, kinetic energy, potential energy, non-conservative work. That would be stuff like if there was a motor attached to the pendulum or like a fan that was blowing it back and forth, that's non-conservative energy. It's like energy being added to the system, and it's just not going to come back. Friction is another one. Damping is another one. Like anything that is not position dependent. But that one, we just said, nothing there. Okay. Oh yeah. Do you use KE for kinetic energy? KE? All right. We're not going to do that just to make your life a little bit more difficult. We're going to say KE is T. Just, again, because. And then for potential energy, do you call it PE? Physical ed? Or U? Okay. So instead of U, we're going to call it V. Again, just to make your life more difficult. Yeah, I would love to like lobby and force and say like, all right, the School of Engineering has this list of constants. Like these are the labels for things like forever. And have everyone just agree V, like a little v is always a velocity or something like that. But it's just me. I'm just fighting windmills over here. So we're going to keep relabeling things. For us, T and V, kinetic potential energy, at least for today, until you rewrite all your notes in your own way. So what is the kinetic energy of a pendulum? Yeah, same thing as everything else, right? 1/2 mv squared. We don't really care about like rotational energy of this thing. Like maybe it was spinning around, but it's not really factoring into our equation of motion. So the main thing is just that 1/2 mv squared. Like how fast is that mass traveling? What is our potential energy of a pendulum? How much potential energy does it have? MGH, yeah, same as everything else, like moving against gravity, right? It's MGH. Cool. And it's always good to start with just the basic definitions like that. Like if you have gravity, then it's just MGH potential, 1/2 mv squared. Now we can build it into, because the things that we know are theta and theta dot. We didn't directly calculate H, so let's figure out how to turn H and V into theta and theta dot. That's the next step. All right. Which one do you want to start with, V or H? Position or velocity? Or speed? All we really care about is speed because it's kinetic energy. So energy doesn't really have like a direction. It's just sort of like a scalar quantity. Which one? V or H? No, yeah. Because we need both. So once we do one, we'll figure out the other one. H. So I have theta as a function of time. My L is constant. What is my H value? Like how much potential energy do I have? Okay.
where it's based on.
Yeah. So we can think about, like, if I take this and rotate it down here, I could say that from the bottom, when theta equals 0, going up to the top, that could be my potential energy. That's like H. I like that. So what is that value of H? It's got to be something with that cosine theta, right? If we start drawing like from like L would be that distance, the total distance from the base to the bottom. L cosine theta is like as theta increases, that's distance from the base to current position. So what's H?
L minus L cosine.
Yeah, just take the difference, right? Because we're just kind of looking at two. If I take one big L step forward and one H back, now I'm at L cosine theta. Cool. So it's still MGL, then I'll take that 1/2 cosine theta. Just dumping out that H. Cool. How fast am I going? What's the speed of this thing? If you're not sure, here, so what coordinate system did we choose when we started building this pendulum? Like, how are we tracking its motion? What was the... Yeah, like a rotational, some kind of like spherical or polar coordinate, but somehow like we have this like theta and r coordinate system. So we can just look up like what is the speed in a polar coordinate system. Polar coordinate velocity. You can also, like, it's in the textbook, but sometimes it's like almost more work. Like, go and find the textbook. But sooner or later, you'll always find the same equation. And if it, at least, we should be able to recognize it. If there's something like really weird about it, like an AI generated polar coordinate, throw that out. So here, R is going to be like distance from our origin, but that's always equal to L. So what's dr dt? If R equals L and L is constant, what's dr dt? 0. So that one's gone. We have no radial velocity. It's not moving in that direction. And then the only one left is that L, so R times d theta dt. So my speed is always going to be L times that theta dot. Nice when things work out that way. I could take the magnitude of it and then, you know, like magnitude squared and then take the square root, but I only have that one component. Nice when things work out that way. So it's L squared theta dot squared. Now I've got those I already calculated as part of my like model. Like I have theta dot, so I can start calculating T and V. And let's go back up here. I'm just gonna grab like the variables that are theta and d theta dt. And when you're dealing with when you're doing math, always leave it as radians. Don't convert to degrees and then try to convert it back. Everything will get messed up. So that one, we don't need any of that. I'm just grabbing that d theta and that. I'm taking that theta that I predicted, say that it's 1 minus mgl times that 1 minus. And let's just give ourselves like a mass, say that it's 1 kilogram. Unless this might be in feet, but that's okay. Now my V nonlinear is still the same equation. T linear take L squared theta d theta dt squared. It's the same equation for the nonlinear. Then now that I have everything kind of plugged in, let's look at what's going on here. Oh, and I'm gonna change it back to small angles because I was playing around with stuff. We were looking at 90 degrees. What did we decide was a small angle? Do you remember? What's your like new rule of thumb? Or if you experimented on your own, where did you figure out like, this is a large angle, that's a small angle. 90 is too big. How small is small? What was small enough? 20? 20 sounds good. So now looking at like theta, there's no real difference in time period for large and small, for like linear, nonlinear. All right, there we go. Now we have potential energy as a blue line, kinetic energy as a red line. Does this make sense? Yeah? What are the things that make sense? Like looking at this.
Conservation of energy says that it should fully transfer between kinetic and potential. So potential is at 0. Kinetic should be at its max.
Yeah, yeah. So it keeps switching back and forth, right? What about the time period here? Because we're only looking at 2 time periods, but down here we've got like 4. Everything's happening like twice as fast. So we like increase the frequency of this. Does that make sense? Or did I do something wrong? Yeah.
One time period, like in the upper graphs, just like from like both sides of motion. So at the so it will be twice as fast on this side because he's going from end to end rather than just one cycle. It's hard to explain that.
Okay, yeah, but yeah, so everything that happens from like 20 to 0, it's exactly the same, at least energy-wise, going 0 to -20 and -20 back. So we have like an extra symmetry axis that when I'm over here moving this speed, then it's exactly the same moving over here at the same speed. So we doubled, basically we're looking at the same thing just happening twice every time period. So it makes sense. Things are looking good. All right, so now let's look at some stuff that doesn't make sense. And yeah, we can look at nonlinear. No difference, like it looks like the same graph. So instead, let's say V lin plus T linear, V nonlinear plus T nonlinear. If I take kinetic plus potential energy, what should this graph look like? Like what kind of function? Just should be constant, right? Should be constant because my law of conservation of energy says that if I lose kinetic, I gained potential, and vice versa. So it's always equal to the same thing. What does my graph actually show me? Is it still constant? Are we getting tricked by axes again? Like in our like 180-degree case? We need to zoom out. Maybe that'll fix it. Where are we going? Like 4.79 to 4.85. So let's zoom out a little bit. Let's go from like 4 to 5. Like min. So I'll change the y-axis to start at 4, go to 5 joules. Or I think it's joules. I don't know. We might have some weird units. But is it constant? What's happening? It's weird, right? Something's off. The blue line is our linear approximation. That red squiggly line is nonlinear. The fact that the red line is squiggling is like, that's numerical uncertainty. Like just, we told a computer to solve this differential equation for us. It's not going to be perfect. Like it's not going to solve an exact equation. It's always like numbers, and there are things called like floating point operations. They stack up. So over time, it'll slowly have random error associated there. But for the most part, it's always like 4.8 joules or whatever that, I don't know. If this is all like feet and something, maybe it's like horsepower times slugs divided by frogs or something. I don't know. I don't know what the units are that we ended up with, but we have units. It is energy somehow. So what's going on with our linear? Why is linear not constant? Is it just not accurate because we have a linear approximation? What is the potential energy of Here, let's do a little bit of comparison of like, what is the potential energy of a spring? Do you remember this one? This one, I mean, we haven't really like covered it, but 1/2 kx squared, so it's like a parabola. So for a spring, for conservation of energy for a spring, for a linear spring, we have 1/2 kx squared plus 1/2 mv squared equals constant. And for the linear approximation, we made an assumption that our spring force, that our spring is a that our pendulum is a linear kind of spring, right? So this became this, like just a linear spring, like that. So really, when we said this is a linear system, we're approximating that its potential energy is 1/2 mgl theta squared. Which is, I mean, that's close to like cosine. Cosine, if you look at it, an upside down cosine looks like a parabola if you're looking at small. And I mean, we could try that out if we want, right? Take this. And now my blue line is an exact straight line, right? Because I'm taking that pendulum that is a nonlinear spring and turning it into just a linear spring, saying that cosine is basically theta squared. And that works. And I don't know, if that's interesting, then you can try it, or you can plug this in. You can either leave it as this 1 minus cosine, or plug that in, however you want to do it. It's your project. I just like to control it, tell you what to do. No, I'd prefer that you just do it your own way. Explore something new. I want to add relativity to this pendulum. Or a Foucault pendulum. Look at like as the Earth rotates underneath your pendulum, where does it go to? Whatever you want to do. All right, so that's one thing that you could, if you like that, you want to try it and go for it, or anything else that you were thinking about that I could help at least show an example of. Main thing is I don't want you to be like, man, I really wanted to calculate something, but I just don't know how to do it in Python. So that's why I'm showing like a walkthrough example of how to take the idea that we wanted to do, put it into like code that we can now plot and interpret, do all the other stuff we wanted to. I know it's Friday. It's like we're so close to the weekend. But I wanted to talk about tension. Oh, tension, like in the pendulum? Yeah, how come you didn't talk about that? It's like, oh, we could talk about that if you want. Yeah, that would be really great. Okay, yeah, let's do that. No? It's okay? All right. You need a puppet. That would help, right? All right, we only had two forces. We know mg, constant force. Tension is whatever it needs to be in order that the system doesn't break. Doesn't always happen. Sometimes the system breaks. Have you seen that video of the people like jumping off a bridge in Tampa? Yeah? No? Have you seen this? Yes? Some yes? No? Do we still have it? There we go. Yeah, I had just pulled it up. So a while ago, 97, yeah. So, in the dark ages before the internet was a real thing. These people all wanted to tie themselves to kind of like a big long, almost like bungee jumping, but they wanted to make like a big pendulum out of it. So they connected the cord to the bridge and then ran down the side. Then they're all attached to each other, and then they jump off. But they didn't do the calculations correctly, so right where kinetic energy is the highest, the cord breaks, and I think no one died, but it was a close call. It was bad. There were a lot of injuries. Things didn't work out very well. I mean, in general, it's not a great idea to jump off a bridge, but if you're going to, do the math first. Make sure you put in a factor of safety, because they factored in the fact that they all weigh a certain amount and kind of gave it enough factor of safety that the cable will hold all the people, but they didn't factor in the centrifugal force that gets generated as you're moving from 90 degrees to 0 degrees with all that increase in kinetic energy. So yeah, word of caution. If you're in Tampa jumping off a bridge, do some math before you jump. All right, so let's do some math. We knew that we had that one equation that theta double dot is always negative g over L, sine of theta. But there was that other equation for our radial direction. Like that centrifugal force term, the mr theta dot squared, that's over in our... I like to always leave it as part of my kinetic diagram so it doesn't get double counted. That's the main reason that I always draw a free body diagram and a kinetic diagram rather than trying to draw my acceleration terms all in one place. So now T is mgl cosine theta plus ml theta dot squared. And we can do that, right? We have theta dot. We can figure out what is tension in this cord at any point in time. And what was it? MGL cosine theta plus, oh yeah, that's what I was trying to do. Now I've got the equation rewritten as Python stuff. And now kind of looking at linear versus nonlinear, if I'm using that full equation for the constraint, where I'm not approximating that cosine theta is theta, and I'm not getting rid of that theta dot term, then they're both the same thing. So we can take a linear approximation and plug in the real values, get a real value for tension. If I start making approximations, like I say cosine theta is 1, and then I say that this is, if I say like d theta dt is 0, like multiply the whole thing by 0, that's where I start to see bigger differences of like, I said the tension was constant, but it's actually gonna like shoot up above that. And it'll drop down below, right? Like there are times when the tension is much lower just because of like where the pendulum's kind of swinging through. Yeah. And bigger the difference. So here, come back up. We can do our bridge simulation. So if we start at 90 degrees on the bridge in Tampa, we can look at difference in period. Things start off with much less acceleration, so at least we had a conservative estimate for how fast we'd accelerate. But then when we think about like how much tension, there's a whole extra like bump. It starts off pretty low, like there's not much tension through most of the first part of the swing, but as we get to the bottom, there's an extra, what is that, 20%? Like jumps up by 20% higher than what we thought it would be. Mostly from that centrifugal force term coming into play. Cool. Anything else? What else is going on for project or? Yeah.
What is the length you have for this pendulum?
This one, that's a good question. Let's go back. I got to scroll all the way to the top. 8.1. So I had changed it to match that 27 feet. So 8.1 was like 27 feet and 7 inches or something. Yep. That's why the time is so long, because it's still looking at 2 time periods.
Are you still looking at 90 degrees?
And this one was looking at 90 degrees, yeah. Yeah, at least from what I had been running through. Yeah, so it is all still newtons and kilograms, because I didn't change it to feet. Yeah. Feet in second. Mm-hmm. Cool. Anything else? Not all at once. One at a time, please. Good. I did shift, like I think yesterday homework 4 was due, which didn't make any sense. So shifted everything to next week. We'll try to get through module 4 homework Monday, Wednesday, Friday, and then work on the project. Then we'll jump into individual work, where you can work on something that drives you, something that's getting you through the class. Like, I need to know how this works. Sound good? Yeah.
Another third question, do we have to like insert more code, or do we just like answer as like in a paragraph form, I guess, about like what other calculations we would do? Or should we like show more code?
So I think like if you were thinking, sorry, as I scroll back and forth and plot, I gotta get rid of. So here's like my kinetic and potential energy added up. Like they're supposed to be constant. Nonlinear is not exactly constant. Linear if I say it's a linear spring MGL stiffness, then it is constant. So this is a great way of saying, of like doing a comparison, like make another plot, and now I have a comparison between those two. Another way you could do it is like we have these values of theta and theta dot, theta dot, theta double dot. So you could pick points on the graph of saying like, okay, the energy should be constant at time 0 and time whatever, 4 seconds. So let me grab the values from there and make a table that says here is time 0, theta is this, theta dot is that, time 4, theta is this, theta dot is that, and here's kinetic and potential energy. And then you're just sort of like doing the same work but in a table. And that would be another way to do it if you're trying to avoid Python, or add a graph. And then I don't know which one's easier though. I guess it depends on the person. 6 of one, half dozen the other. But the main thing is like practice. As engineers, you're paid for numbers, so graphs are a great way to show like a whole bunch of numbers all at once. You can compare between them. Tables, I think, are harder to read, but they do present like very precise comparisons between numbers because you always see the exact like calculations that you're kind of trying to plug in. So tables, graphs, bar charts, but somehow like practice doing some quantitative comparisons. Thanks. Yeah. Anything else? All right. Have a good weekend. Thanks.